this. All right. So this is the little application that we've got running. I'll make a few RenderDoc captures for you, so you can dissect it, and I'll also probably open up in RenderDoc as well and go over it in RenderDoc because it's easier to see what's going on. But generally speaking, since the last time we talked, we handled a few things, such as what happens if you have multiple textures that have different formats. So, for example, compressed, different kind of compression, RGBA versus RGB, a whole bunch of stuff, and how to make that work with stuff that doesn't support the divergent indexing. Right?
Okay.
So, because you know that you just can't have an array of textures and index them with a random integer, right? Unless you have that descriptor indexing extension in Vulkan. And if you have descriptor indexing, you might as well use bindless anyway, and descriptor indexing is not a thing on mobile, so there's basically no way to get around that. Excuse me. So there's no way to get around the fact that you need to index with uniform values. Okay. I'm just gonna build it again because I made a few changes recently. Cancel. Okay, so so we did a few changes. We also actually went and did the packing of the mip-tail into like handling of how you handle mip-map levels, which are smaller than the page size, and just general usability, figured out how to do the mip mapping and everything like that, because it's a little bit different actually to how it would work normally. So the main thing we're doing now is that we're so it's running. Okay. So it's gonna take like a minute to load the textures because it actually needs to do the mip mapping on them differently. You can pre-compute the mip maps, but it's just gonna be a different sort of mip mapping than you would do normally. Okay. So so here it is. Damn it. Okay. Okay. So I can't find my window anymore. Oh, here it is. Right, so I don't know if you can see because obviously the screen is smaller in this instance, but
I can see.
Yeah.
Really?
Yeah. The textures, they all work fine, more or less. Any sort of aliasing you see might be geometrical or just from the bump map itself. But if you just fly around the scene and have a look at it, you're not really seeing any seams or any problems with anisotropic filtering. It's more or less working properly. If I actually disabled the bump maps, there'd be no aliasing at all because what you're seeing is mostly specular aliasing. But the most important part, you've got no bleeding from neighboring tiles. So I'm gonna open this up in RenderDoc, and we'll see what's going on. Okay, so RenderDoc, I'll launch application. And
Well, maybe just open the capture instead.
I don't have a capture yet. I have an old capture, but I don't have a capture with new stuff. Okay, and launch.
Well, I have a question about mip-map generation.
Mm-hmm.
Uh, is GPU mip-map generation is faster than CPU, and why do you use CPU?
Well, in this case, we used CPU for mip mapping because it's just the way that our engine is made is that we want to be able to do stuff independent of independent of the graphics device that is currently like attached to the computer that's currently running. So it's just for repeatable results because I want to run this on servers and stuff. So in my case, essentially, what happens is that I want to run this whole thing independently of anything else.
Okay.
But for your case, you can do the mip-map generations on the GPU. But the problem is that on the CPU, it was like a lot easier for me to do because I already had all the conversion functions between the different formats. So I could do the mip mapping because mip mapping requires conversion to floats and linear, linear light spaces. So you actually need to decode all of the different formats that your textures might be in, which is a little bit difficult if you're working on stuff that it's, for example, compressed or sRGB or something like that. So first you need to like decompress it, then do all of the filtering, and then you need to save it back to that format, which is a little bit of a big. It's a complicated shader to write.
Yeah, I see. Okay.
So it was easier for us to write because it took us 2 weeks to write actually all of the stuff that actually does the mip mapping. But if you really wanted to, I don't know, cut down on the load times or something like that, then sure, make it in a compute shader. But in this case, it was just easier to write on the CPU and debug it on the CPU.
Yeah.
Because
you can consider to provide a standalone application to generate offline mip-map based
yes,
on your lab.
but the difference here is that due to how you're allocating the memory in the virtual texture and how you cannot allow for 2 pages to share the same virtual texture kind of area texel pointer, you need to round all of the textures that you're going to be allocating to a power of 2 and square. So there's basically there's just 2 ways to do it, and one of them is that you stretch the texture. So for example, let's say let's say I make myself a texture, and this texture is like this, right? And actually, I'm gonna make it a little bit lopsided. Okay. So let's say that this is my texture, and it's obviously not square, and it's not power of 2, right? So in order to put it in the virtual, in the virtual table, which would be, for example, a perfect square as we already established, because it needs to be a perfect square. I run into a problem because I obviously need to pad this to a power of 2, right? So the allocation for this red thing actually needs to take up all of this big square, right? There's no way around it, right? So all of this blue area needs to be reserved for this for this texture, which is not power of 2 or square. basically I need to stretch it to the next power of 2, which is also a square, right? And there's two ways for me to handle this, right? One of them for me to handle this is to take this texture, right, and then stretch it. So it fulfills this criterion, and then after it's stretched, I do all of the mip maps as if it's a square and power of 2 texture, right? But that's a little bit wasteful because, for example, I can have very long and thin textures, and then I'm just, increasing the resolution with no need. Because, for example, I could have a 1 pixel thick texture, right? Which is just a really long strip, and now I have to like make it 2,000 times as big. Because let's say it was 2,000 pixels by 1 pixel, and now if I have to stretch it, then what it means is that first of all, I'm making it big, and then all of the stuff that I've actually made right now, I need to make resident. Whereas in the case of this, when I'm not stretching it, but I'm applying some corrections for sampling, then I don't need to make all of the blue area resident. Like, those pages don't need to have an allocation backing them. I just basically need to round up to the I need to round up to the next multiple of a page. So if the pages are, I'm gonna do a little bit thicker. So if the pages are, for example, like this, right? Actually, I'm gonna do a little bit better. So if the pages are, let's say there are 4 pages here, right? And they're more or less like this. Then I only need to basically, if I've got any page partially intersected, then obviously I need to make it resident, but I don't need to fill the ones that are completely not intersected by the texture, right? So in this case, for example, all of the stuff that's up above here, like for example here, all of those tiles above, they don't need to be filled. But obviously, since we're talking about partially intersected pages, then obviously this one needs to be allocated, 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 and that one. But at least the rest, that's completely not touched by the textures, they don't need to be allocated. But that introduces a problem because obviously there's the whole filtering issue. So when you're preparing this texture for upload, you need to replicate it a little bit. So essentially what needs to happen is for the tiles that you are intersecting, you need to fill them out a little bit with the border color. Depending on your original texture's wrapping mode. So if your texture's wrapping mode is repeat, then obviously you need to repeat. If it's mirror, then you need to mirror. If it's border, clamp to border, then you just need to like stretch the border colors. But generally speaking, there needs to be like a little, there needs to be a little band around it. So what we do is we actually, when we compute the mip maps, we actually take this original texture, right? And what we do is what we do is we actually fill out, we don't stretch, we fill out the big texture with whatever wrapping mode you have. So for example, in this case, we're looking at the repeat mode, the one which just repeats texture coordinates. But if your original, if your original texture was to be sampled with a different wrapping mode, such as, for example, clamp to border, then we'd be just stretching the border pixels, right? If it was mirror, then we'd be obviously, mirroring the texture around. But the wrapping mode that I'm showing you right now is just repeat, right? Sorry about my bad pasting. There's not supposed to be any blue in between the reds, but maybe it's easier to see what we're doing that way. So once we actually have this padded copy, we actually have a special CPU side filter called padded copy. So once we actually have this padded copy, what we do is we actually mip map this.
Yeah.
And that produces consistent results, because the problem is that normally if you compute the mip maps for a texture which is not power of 2, then you have a rounding down behavior. So for example, if you have 513, right, as a side length, then your next mip map level size is going to be 256, because it's rounding down all the time.
Yeah.
Right? And then it's basically division by 2 all the time, but it's knocking off any remainders. But if you do pad a texture like this to a power of 2 and put it in a bigger texture, the problem is that when you start to mip map the texture, the line between the original I'm just going to show you the line between the original and the line between the original and the padded. So this line here, that's actually gonna be in the subsequent mip maps is gonna be halfway in a different pixel. So what it means is that it's actually gonna have the behavior of rounding up, contrary to the spec. So you need to compute the mip maps in a different way. If you're going to use Photoshop or GIMP or something like that to compute a KTX file or a DDS file that already has all of the mip maps inside it, then you're going to have a problem, because this is not appropriate. Because everything is going to be offsetted slightly by fractions of a pixel, which normally wouldn't be a problem, except that fractions of a pixel in really high mip map levels, that's actually a lot of pixels. So what needs to happen is that you need to round up the mip-map levels. So if you have a 513 texture, which has a dimension like that, the next mip-map level is going to be not 256, it's actually going to be 257. And then the next mip-map level of that is going to be not 128, but it's going to be 127. So it's actually going to keep on growing, if you get what I mean. And this is going to have a interesting kind of situation where every single time you scale the whole thing down. So I'm just going to grab this and actually I'm going to scale the whole image. Scale image. Okay, so you'll notice that every single time you scale this whole thing down and do the mip map, this edge thing is going to keep on drifting out. So normally, if you had what was the original size of this texture? Yeah. So normally, if you had, like, for example, a 513, then after 9 mip-map levels, you would expect it to be a 1x1 texture, but with this logic, because it's rounding up all the time, it's actually going to be a 2x2, right?
Yeah.
So you can see that this edge just keeps on drifting to the right, and that's the reason why the mip map needs to be computed completely differently. And this is why you cannot compute them offline with your standard tools. That's why we had to write all of this extra CPU mip-mapping code. Because I can't just have it mip-mapped into a KTX, because the KTX, or for example a DDS, any sort of preloaded texture is going to be using the round down method, not the round up.
Okay, but so we don't really have any way to make to implement virtual texture mip mapping to behave like the standard.
Um, well, it does behave like the standard, but there's like a whole bunch of emulation going on.
Okay. Yeah.
So yeah, so it's mainly to do with the fact that it actually it performs better than the standard mip mapping because NVIDIA had a paper some time ago, like 20 years ago. They had a paper about just have to close everything down. Where's my window? Okay, I think RenderDoc might crash. So the main thing with the paper that NVIDIA had 20 years ago, it was actually suggesting, it was going on how to handle mip mapping of textures that are not power of 2.
Mm.
I think I linked it some time ago. I'm just gonna find it maybe. It's called NVIDIA mip mapping. I might find it quite quickly. Non-power of 2 mip mapping, that's the one. It's a white paper from a very long time ago. I think GeForce free days, 2003. So it's going over power of 2 mip maps and it's going over non-power of 2 mip maps. And it's basically saying that there's two ways to handle non-power of 2. There's one way you do floor, which is basically rounding down, and there's one way you do seal, which is rounding up. And essentially what's going on is that with this rounding up thing, you actually end up with one mip-map level extra on non-power of 2 textures. Because when you're rounding down, a non-power of 2 texture has the same mip-map levels as a texture which is the next lower power of 2. So if you have 100, if you have 127, then it behaves as if it's basically 127, and then the rest of the chain is the same as for a 64 size texture.
Okay.
Sorry, wait, my bad. Yeah, so if you have a 127, then it's gonna have the same number of MIP chains as a 64 texture, right? But obviously the size is gonna be 127, 63, 31, 15, 7, 3, 1. But if you have a rounding up methodology, it's gonna actually behave like the next power of 2 up. So you're gonna end up with one more mip-map level. Obviously, for power of 2 textures, whether you're rounding down or rounding up doesn't make a difference because there's nothing to round, because you're always spot on. And this paper actually goes through saying that it would be NVIDIA's preference if mip maps could be rounded up instead of rounded down, because the quality will be superior, as in the quality will be just as good as using a power of 2 texture, right?
Mm.
So technically speaking, we've made NVIDIA's dream come true. Right?
Yeah.
So it's how they wanted it 17 years ago. What's it called? Damn it. The map maps are rounded up, but the problem is that you won't be able to upload the texture to the graphics API, tell the graphics API to do the mip map for you, or do the mip map how you're usually doing it, download the results and then pack it into the virtual texture, because you're always going to be off by a few pixels.
Yeah.
So one way to fix this is obviously do this on offline, and instead of putting it all in one okay, RenderDoc decided to be weird. I'm gonna try with a newer version of RenderDoc actually. So basically what's happening is that you could either say we're not accepting any textures which are not power of 2. If you only accept power of 2 textures, everything is fine. You can compute the mip maps with whatever tool you want. You can pre-compute them, you can compute them at runtime. You don't have to change anything with power of 2. Absolutely
Okay.
no, it's not necessary, right? At all.
But it doesn't have to be square, right?
It needs to be power of 2 and square.
Okay, power of 2 and square. Yeah.
I think you could make it work with power of 2 and non-square. That is possible, I think.
Yeah.
But I haven't thought about it. I just thought about how to make it work with all cases. Your working texture would, for example, be 2048 by 2048, quite huge. Where, for example, your image might be only like 1 by 1027, right? But you need to do the mip map on that, and then after you've done the mip map, you can compute the rounded up mip map sizes and throw away the data you don't need, right? So either you pad the thing, save it to a KTX as padded, add some metadata about the fact that it's actually a smaller texture, compute all the mip maps, and then load that, store that on disk, or basically instead of having all of the mip map levels in one KTX or one DDS, you have one image per mip map level, and then the mip map levels are allowed to be vastly different sizes. But that's only about the disk storage. To set an environment variable in our engine that overrides the list of available extensions, because RenderDoc lies about some extensions, as in it doesn't whitelist certain things because it doesn't know what they do, so they could crash the thing or just basically make the replay unreliable. So it only lets you know about the extensions that it can handle, which is obviously in this case it's a problem because we rely on a few extensions to do the divergent indexing.
Okay.
So if we go to our texture viewer, this is the thing that has been rendered. You can see that we got the material slightly wrong on the vase, but that's not a problem with the texture, that's actually a problem with the material that we read from the OBJ file. So anyway, you can see that it's drawing one by one. Oh,
Yeah.
see,
Yeah.
that's our vase. Obviously that's the rest of the stuff. So you can see the textures on the right, and this is the way that we've done it here to reduce the divergent indexing. Alright, so I'm just gonna go halfway here. So
Okay, but first, what is divergent indexing?
okay, so I'm gonna go to the pipeline state and show you exactly what I mean. Okay. Alright. So here's a bunch of stuff in our shader that doesn't really have to do anything with the index with the virtual texturing, but this is the virtual texturing, right?
Okay.
So we've got the page table. We've got the physical textures, the texture views actually. For every single format you wish to use, you need a separate texture view.
Ah, okay.
Okay? But the page table we actually managed to share between all of the formats to reduce the divergent indexing. And right now in this shader, because we actually say up front that we require NVIDIA GPU Shader 5, which is an OpenGL extension that allows you to do divergent indexing just how the non-uniform keyword in Vulkan lets you do that. So we don't particularly have a problem. The main problem we have is that, for example, we have this is not very legible because it's been translated by GLSL lang to SPIR-V and then back from SPIR-V into GLSL with SPIR-V cross. So there's a bunch of extra variables which weren't here in the first place. But for example, so we've got this texture grad, yeah, right? and it's getting a physical storage format view, right? And it's getting it with this lovely little variable, which basically tells you that it's an evil variable, aptly named 666. Because basically what it's doing here is actually it won't pass on a bunch of GPUs. So you've got a physical tile text storage format view, right? And here it's an array of texture arrays.
Okay.
Right? So that's 3 separate textures in an array of textures, right?
Okay.
And this is becoming a problem because I think I've just spotted a bug actually. I'm just gonna write to Chris. Okay, this is clearly a bug. So essentially what we have here is that this is 3 separate textures, 3 separate descriptors, and you're not allowed to basically index them at random like that. You're allowed to index them with another uniform or some sort of a variable which stays constant for all of the invocations in the shader subgroup. You know, the warp or whatever it's called, the bunch of stuff that runs in parallel, right?
Okay.
So so in this case, because we've got this NVIDIA extension, it actually allows us to do this, right?
Okay.
But it's not really allowed on other GPUs. And I've
Okay,
actually...
but
Mhm.
so why will we make this portable?
Okay, so how we make this portable?
Yeah.
Show you with... Okay, that's the one. So we've got like a really big kind of include for shaders in our engine. You know, just write include and it's get included. There's a whole bunch of stuff that you can configure. One more second also.
So you emulate that extension?
Yeah, kind of. So what we do is actually we've written a patch for SPIR-V cross which lets you use non-uniform and actually emits the NVIDIA extension when you are caught using non-uniform, because before it would just fail to downcompile the SPIR-V into GLSL. But in our case, what we do is essentially we enable this extension. This is a SPIR-V extension. Don't pay attention to this NVGPU shader thing that we're checking for. So this NVGPU shader thing that we're checking for, you don't pay attention to that. That's just to do with our engine. We messed up a little bit. Normally, in SPIR-V you'd be enabling this extension, non-uniform qualifier, and then because SPIR-V cross doesn't actually implement the subgroup operations, we actually opened 3 issues with SPIR-V cross about that, and I think we're gonna have to make some pull requests. But basically, it's not gonna compile the shader subgroup stuff from SPIR-V down into GLSL. So that's just basically stuff that's to do with how we translate Vulkan shaders into OpenGL shaders. But for you, it shouldn't be a problem. Everything you need to do is just enable this GLX non-uniform qualifier.
Okay.
But the problem...
So basically, we will have to wait for another SPIR-V cross version that's supporting this extension, so we can use.
In my case, yes. In your case, no, because you're on Vulkan.
Okay.
So in Vulkan, you do this non-uniform qualifier enable, and then
Okay.
all you need to do is when you come across some divergent indexing, is you just need to mark it up that it's non-uniform. So if you have a look at this thing, this non-uniform qualifier. So if you have this extension, then all you need to do is you need to wrap this index, which is going to be non-uniform, in this non-uniform qualifier here, right?
Okay.
So that's actually going to make this thing work all right.
Okay.
So you're indexing this array, but then you put this non-uniform qualifier and everything's fine.
Okay.
But the problem is that on mobile, which doesn't have the descriptor indexing extension, it's also not going to have this non-uniform qualifier extension.
Okay.
So what we do here is actually we don't compile our shaders to SPIR-V straight away offline. We actually do it at runtime, because then we can inject some defines into them wherever certain extensions are available. Like, for example, here.
Okay.
Right? So if the extension is not available, then we have to do this emulation, which is actually a little bit annoying. So this is actually written in OpenGL. It has to be written in SPIR-V. But the general idea is more or less the same. So what you do is you need to ballot which threads, this ballot thing, you need to ballot which threads are currently alive, because it might be that you're in this function with only some threads which are alive. And then while some threads are still waiting to sample from the texture, you need to be in this loop. And then you need to elect an invocation. SPIR-V subgroup extension actually has a nice elect function, which will only be true for the very first alive invocation in a group. So you need to elect the invocation, right? Which I'm doing here, because I haven't got this thing down properly. So you basically you elect the first invocation, which is still alive and hasn't sampled yet, and then you read this index from that invocation, right? So all invocations which are alive now have the same index, right? And then if the index that they read from the elected invocation, the very first one, matches the index that they wanted, then they can sample from the texture.
Okay.
So basically, I'm gonna just write it down. So imagine you had like, we're not gonna do 32 or 64 wide warps, because it's gonna be way too much typing, but let's say it's an 8 warp. So some of them are dead, some of them want index number 0, some of them are also dead, some of them want index number 3, some of them want index number 2, and then another one's wants 3, and then another one's, the last two want 0, right? So this is what I mean by divergent indexing, right? So they're all running in parallel. Normally there'd be like 16 or 32 or 64 of them, but in our case it's 8 for this simple explanation. So what happens is that here you need to see. Yeah, I'm just gonna put that. I'm gonna put it up here. So here you've got the outstanding sample mask. And what that's going to do is basically for every single invocation that's still alive, that's not dead, it's going to give you a 1, right? So you've got a 1 here, and then you've got a 1, 1, sorry, you've got a 1, and a 1, and a 1, and a 1. Yeah. So this is what your outstanding sampling mask would look like, right? And then if this mask is not 0, as in there are still some alive masks, you go in, and then you need to read the first invocation, right? Which is not dead. So in this case, it'd be where the first one is. That's why there's a find LSB here, find least significant bit. Just by the way, I'm just gonna make a note that I'm doing it least significant to most significant in this direction, which is not very natural, but okay. And then you need to basically elect the first alive one, which in this case would be the second one, so with index 1, and you need to get the format, yeah, the index that you're going to sample with. So here you get a 0, right? And then you basically need to get if you can sample, so if the format is equal to the format. So in this case it would be, obviously it would be 0 for all of the dead ones, then everywhere where it equals 1, everywhere where it equals 0 it would be 1. Right, and that's exactly what you'd get. And then you'd get a mask like this for all of the threads, for the invocations, and then they would need to be so this is your mask which can be sampled, and then you need to disable the outstanding sample mask, which is here, with the ones that you're about to sample. So this one gets deleted, and this one, and this one. And then you, if you can sample, so only these would go in, only these 3 would go into this part, and then they would actually be doing the sampling from the textures with this subgroup format ID, which if the compiler is remotely sane, it knows that if you're doing this read invocation thing, it's going to be the same for all of the invocations. So now this is going to be the same number for all of the threads which actually get to this point.
Okay.
So you're not going to have divergent indexing anymore.
Yeah.
And then basically what this would do is it would read your color into your thing. So you've got a dead invocation, and then you've got your color, and then you've got your dead invocation, and then you've got nothing yet, we don't know, and then you've got your color, right? And then you go back to the while, right? The outstanding sample mask is still not 0, so then you go through the whole cycle again. So you elect the first one, which is still outstanding, right? So in this case you would be electing the fourth one, which has an index of 3, and then you need to mask out all of the ones which are not equal to 3. So in this case it would be only the fourth one. Oh, sorry, and the sixth one, right? And then these two would actually get cancelled out from this outstanding sample mask. And then you go to this can sample, and then you basically go into this texture sampling thing again, and then you fill out the color again. So you've got the color, and then you've only got one outstanding sample, and then you elect it, and then your sample mask becomes here. And then you go through this, it all zeroes out, you finally get your last color, and then all of the invocations have their correct colors, and this outstanding sample mask is now 0, and you can continue with your life. So this is how you basically, with using those subgroup intrinsics, which are very basic because they've been introduced in OpenGL a very long time ago, so there should be on mobile, especially the ones about electing and balloting, really, really simple intrinsics, and then basically what they would do is enable you to emulate this non-uniform indexing thing.
Okay.
Yeah.
So which documents should I read about this emulation?
It's something that we actually we needed to invent for the purposes of this.
Okay.
I posted it a few times in the academic resources on Discord, but yeah, we're gonna rewrite it at some point into the Vulkan form. But it's pretty simple to rewrite into the Vulkan form. I mean, you just you replace this find LSB with something else, and then there's actually a find LSB for with the subgroup intrinsics. You replace this ballot with something else, and then you obviously do this elect thing, and this read invocation is slightly different, but the whole format is the same. You just basically want to read the spec for GL KHR subgroups or something like that.
Okay.
Yeah, it's not really a long document. Also, the issues that I opened on Spear v Cross might be a bit enlightening. So basically, this is really complicated, and this is on AMD. This is also not very performant. I think AMD basically translates this non-uniform thing into this because it actually, I think apart from RDNA and RDNA2, it can't actually do divergent indexing on GCN. So it actually, the compiler actually does this behind your back. So this is the reason why we've decided to share the page table for all of the texture formats, right?
Okay.
Because when we share the page table for all of the texture formats, right, you don't need to divergently index the page table. And basically the way that we do it is we have this page table. I'm gonna switch to RenderDoc. So this page table that we have here, sampler 93, texture 95. So this page table that we have here, we actually divide it so different layers, because it's a layer texture. It's a 2D array. So different layers are assigned to different formats.
Okay.
So this layer number 0 would be assigned to some format. I'm not exactly sure. I can check. Give me a minute. Okay, buffer. Let's see. Okay, so layer to sampler index. Okay, so layer number 0 is assigned to the sampler number 2, and all of the other layers are assigned to sampler number 1. Yeah. I think I just found another issue. RAU norm, okay. Okay. Yeah. So essentially what's going on here is that we've got those free texture views, right? So we've got first one is for grayscale textures. As you can see, there's nothing in there. Nothing has been placed inside there. I think that's a bug, but because I think there is at least one texture that should be here, but it has been allocated. And then the second one would be an sRGB texture, but with no alpha.
Okay.
So you can hear that. You can see here that the textures have been placed inside, right? And due to sampling precision issues, which is basically you don't want to be making a huge 16K by 16K physical texture because of the way that floating point coordinates work. In the top right hand corner of the texture, you would be having problems getting the appropriate sampling precision because a difference between two big floats is less precise than the difference between two small floats, right? So that's why we basically capped it to be I think somewhere between 16 pages along the bottom. So in this case, in this scenario, our page size is 128, but it has a padding of 8 pixels on each side to allow for 16x anisotropic filtering, and then we allow for 16 pages in X and Y to be placed inside of a physical texture. So this is 16 by 16 pages, and if you want more pages, we don't make the texture bigger, we actually add more layers to it. So here you can see that we've added more layers to this physical texture, right? And it's all to do with just better quality, like a better quality sampling, right? Just to make sure that the coordinates are nice and precise as they would be for individual textures. Because if you pack too many textures into one big texture, the quality of the the textures that are in the top right hand corner, it degrades because you're not able to do precise interpolation anymore. You know. Okay. So you can see that we actually have a lot of layers in here. I think we managed to fill up 13 layers. And then we also have this RGBA texture here, which has an alpha channel, and that's basically packed the same way. And that something has a very few textures, so only 2 layers are filled in. And that's it. But the cool thing about this is that we only have one page table. So we only have one page table, and you can see the mapping here in the buffer layer to sample index is that the first layer is mapped to the RGBA textures, and then the 5 next layers in the virtual page table are mapped to the RGB to the RGB sRGB, and then the rest of them is just invalid values. And we support up to 256 layers in the virtual table. So the virtual table here, let's get back to this texture viewer. So the virtual table here is 32 by 32 pixels, and then it's also can be up to 256 layers. And the virtual table we can actually make a lot bigger sideways. There are obviously some limits due to how we pack. We actually pack this whole thing into 64. We pack the whole pointer to the texture into 64 bits for reasons of efficiency and compatibility with some certain bindless texturing approaches where the handles are 64 bits. I think with 64-bit handles is nice. So basically we put a limit on the number of layers in the page table and also the size of the page table. But overall, I think let me have a look. Because I got an unpack virtual UV. Okay, so we allowed for 1 second. Okay, text data. Okay, so we allowed for, if I remember correctly, I'm just gonna have to look in the C++ for this. Virtual texture. Virtual texture. Okay, so aesthetics. Okay, so we allowed for 8 bits for the page table X offset, 8 bytes for the page table Y offset, and then 8 bytes for the page table layer. So the maximum size of the page table is 256 by 256 by 256, which is still a lot of it's a lot of texture space, because remember that the smallest I advise making a page is 128 by 128. So if you multiply that by 256 and 256 and 256, that's gonna be 274 billion pixels. So that's still like far more that's gonna fit on your disk. Well, I mean, you could most probably fit more on your hard drive depending on the compression, but generally speaking, it's 256 gigs at least for something that's DXT compressed. And obviously that's for the smallest page size. You could turn up the page size to 256 or 520 or even 1K by 1K if you really wanted to, if you want to huge stuff. And the reason why it's 256 by 256 is one is that mobile Vulkan Mobile, the maximum number of layers in a 2D array on some mobile chips is 256, so we don't want to go over that. And the other reason is that if I can have 256 pages across the bottom and across the top, you know, in the X and Y direction, and my page size is 128, that's basically the same as having a 32K by 32K texture. And the problem is here that I'm actually going to be operating with those virtual UV coordinates, which are going to have exactly the same issues with regards to precision as having a 32K by 32K texture. So you're going to be losing precision on the interpolation, and you might even see some bad interpolation artifacts if you make a virtual table that big. So this is actually why in this example we've kept this down to 32 by 32 and has been actually been using the whole 256 by 256.
Okay.
And
so each text so in this page table it stores the pointer to the physical table.
Yes, exactly.
It points to a tile.
Yeah.
Or it points to the start of the tile, or...
Yeah, exactly. It points to the tile. So here we're in layer 0, right?
Okay.
And the page table is the only texture that has mip-maps in this whole thing. No other texture has mip-maps. Okay. So we're on layer 0, which is all assigned to this RGBA texture. This one. Okay. This one here. So if you click on this pixel, it says that it has a value of 0, 0, right?
Okay.
And what that means, this is an RG16 uint texture. So in our case, what this means is that this page table it's pointing to is going to be... Actually, I'm going to go on RenderDoc because it has syntax highlighting. So I need to go to the correct... Okay, so we've got this vTexture helper. This is where we're getting our page ID. Okay. So we're using the virtual UV in the virtual space. It's a normalized coordinate, which is nice because then we don't need to care whether, you know, we're in the virtual UV space or whether we're in page table space. You know, the minimum is always 0, the maximum is always 1.
Yeah.
So we get the page table, we get the appropriate level of detail, and then this page ID, it has 2 numbers. For the minute, we're only going to care about the first one.
Okay.
The second one is special. So we've got this page ID X, right? And it's going to be using this page ID 497.
Okay.
And it's going to be using this as a parameter to this unpack page ID function. And here's getting the page ID. It's only a 16-bit integer. It's not a 32-bit integer. And the first 4 bits are for the XY coordinate in the physical texture. So as I said, the physical texture can be 16 by 16 tiles. And then the last 8 bits is for the layer, right? So you can see here that if this value is 0, 0 here, then it's telling us that it's, you know, the physical texture number 2, and it's going into wait a second, it's going into this texture, and it's basically saying that it wants the very first 0, 0 it wants the very first 0, 0 tile, right? So it's actually going to be getting this tile over here.
Okay.
Right. This one.
Yeah.
And then obviously, you know, you go the next pixel over. I'm just gonna go on the red. Yeah, you go the next pixel over, and then it's got you've got a 1, and then you've got a 2. I'm just gonna make this a little bit easier to see. Okay, now it's easier. Yeah, so then you've got a 1, and then you've got here you've got a 2, and then you've got a 3, and then a 4. It's pretty standard stuff, and it's just basically mapping this texture into this tile here. Yeah. I'm just gonna have to actually up this even more. Okay. And it's a pretty easy translation, because basically it's 16-bit integer. First 4 bits is the x along here. Next 4 bits is the y. No, up, down, y, and then the last 8 bits is basically the layer, right?
Okay.
So you go to a different layer. Now the most interesting part about this whole thing is how we handle the mip maps. I think you can see the mip maps actually. You can see them here.
Yeah. Yes. Yeah.
Yeah. Okay. So this tile on the left is actually the very last. It's the very last mip map to have a whole tile to itself. Right?
Okay.
It's the very last one. So, as you can see, it has a padding of the 8 pixels on the top and on the bottom. You can see that it's a bit stretched on around the edges.
Yeah.
Right? So basically, what happens is that in this virtual texture, right, that we have on here, I can pretty much tell you that these 4 tiles at the bottom, right here, these 4 tiles are a 512 by 512 texture of these flowers, right? And when you go down a mip-map level, now it's a 256 by 256, and then you're going down another mip-map level, and it's a 128 by 128. And if you look at the value, hang on 1 second. Yeah. So it's got a value of 20 and 21, right?
Yeah.
So 20, yeah. So the first value is 20. So that's actually it's actually going to be 15 plus 4 plus 1. Okay. So the first, I'm just going to have to go into programmer mode. I'm not that good at. Okay. So the first 4 bits that I said were the x value, right? So that's 4. So we've got 1 tile, 0, 1, 2, 3, and then 4.
Okay.
And then the other one is 1. And that should take us. Sorry, just give me a minute. Okay. Yeah. So 0, 2, 3, 4. Sorry, it's not the flowers. But anyway, so it's 0. So it's 4 along the bottom, and it's because it's the third bit is set, and it's 1 along the top. So 4 times 144, which is the size of the thing with the padding, it's roughly here. 576 around here, and then 1, which is gonna be 1 tile up. So this is actually the thing which actually has the whole This is the very last tile that contains a whole mip-map level. Right?
Okay.
And once you go below that, there's a need to pack all of the remaining mip-maps into a single tile.
Okay.
So because there's only two ways to fix this. Actually, there were 4 different ways to fix this. One of them was to have a page table for all of the stuff that is still big enough to have a whole physical tile for itself, the mip-map, right? And then have another page table for the mip-maps, one that would be an array, because all of the sizing constraints would be violated. And then use that, but the problem would be that you'd have to do divergent addressing, because depending on which mip-map level you are at, you would have had to choose which page table to use, which would have been bad. The other one was to I don't even remember them because they were so bad. The other one was to calculate full mip chains for the pages. So instead of having the physical textures right now have no mip maps, they would have full mip maps up to the amount of mip map levels that a page would have had. So it's 128, then it would have had 7 mip maps. But then you'd have this texture bleeding problem again. So in the end, we decided that the only way to actually fix this reliably and properly was to pack all of the mip maps of the tail into one tile. So the last tile is 128 by 128 plus padding, and then the remaining mip maps of the texture are 64, 32, 16, 8, 4, 2, 1, right? Plus the padding. So you can see that they're not exactly following this whole size pattern, because, for example, I believe this one right here, that's a 1 by 1. That's the very last mip-map level, but that has 8 pixels of packing on all around it. So it's actually 9. It's a 17 by 17 pixel thing, because of all of the extra padding for anisotropic filtering to make sure that its neighbors, all of the stuff around it, doesn't bleed into it, right?
Okay.
So I think Cyprian, one of the guys who works for me, he wrote a nice little algorithm which you can copy, you can take it from me, that actually finds the packing of what's it called? It finds the packing of the mip maps with the padding inside one big tile. And I think it works something like this: that first you put one in the middle corner here, and then you alternate. You put one in here, in the corner above. You put one in the corner below, and then you go left, right, left, right, left, right until you basically fill the whole thing. And it will always manage to pack stuff as long as your padding is not absolutely huge. So you can see that there's a little bit of space left. But I don't think you'd be able to use, for example, a 128 by 128 page table size with 32x anisotropic filtering. You wouldn't be able to do that, because a mip map of size 64 by 64 padded by 16 pixels on each size for 32x anisotropic filtering wouldn't fit anymore inside this, right?
Okay.
So in this case, if you wanted to have 32x anisotropic filtering, you would need to use a page size of 256 at least 256, no smaller.
Okay.
Yeah. And the way that we actually compensate for this whole thing when we're sampling, it's not a lot of extra code. We need to go to the virtual texturing stuff. Is the way that we compensate for this whole thing is we actually pre-compute certain offsets because you need the offset in a tile anyway to deal with the padding for anisotropic filtering. So you'll see this virtual texture helper function, and it takes your virtual UV. It gets the page table stuff, and then what happens is that we add the packing offsets, right?
Okay.
So depending on the level in tail, right? So as long as you're not in the, as long as you're in the mip-map, as long as you're in the mip-map levels which have their own page table allocation all to themselves, then this level in tail value is always going to be 0.
Okay.
And then this packing offset is always going to be, +8 and +8. And then as soon as you start going into this packed page, which has all of the tail stuff, that's when you start using different packing offsets. And those packing offsets actually, in our case, because we wanted to have everything flexible, those packing offsets are a constant array of vec2. So because our page size is 128, we know that a texture of size 128 by 128 has, I believe, it has 8 mip-maps levels, because there's always one more. So plus the fact that we're going to be using it for bigger stuff. So this array only has 8 entries of the offsets, and those offsets get added, later on here, and then you finally figure out the sampling coordinate in the tile, right? And that's pretty much it on a special mip-map handling. And this is the reason why the page table is an RG16 texture, right?
Okay.
So in this case, we've got this green channel, right? I'm just gonna put this green up. So essentially, whenever this, because 65535 is our invalid value, it's not 0. So when you see 65535 means unallocated. So most of the time, the second channel of the page table is going to say it's not allocated, right?
Okay.
Except that when you reach the last mip-map level. And you can see here that we actually allocated. We allocated to tile number 21. Yeah.
Okay.
So the way that you know that you're in the last, mip-map, is the fact that the second coordinate, so the second variable in the page table is no longer invalid. Once the green channel starts being valid, that means that you've got a page tail. And you can see that this 21 is basically it's 4 along the bottom. So it's not 4 along the bottom. It's 16. Oh, fuck. 21. Okay, so yeah, so it's gonna be 5 along the bottom and 1 up. Yeah, so it's gonna be this one. And you can see that that's actually the thing.
Okay.
So that's the reason why we made the page table be able to hold 2 values, right?
Okay.
So it needs to be able to hold 2 values, and I think in the future it will be useful for us to, for example, use the second value, because it's not often that we use it here in this case. It's most of the time it's going unused. Like if I just cycle you through the pages, it's completely unused. There's just all of the time where you can see that it's like bright yellow. That means it's unused. So in the future, for example, when we would do streaming, we could, for example, use this additional green value to provide backups. So, for example, if the mip-map level that you want, the high-resolution image, is not available, then the green channel would store like a backup page that you could sample from. like a basically lower resolution thing that you can use for the time being. But for now, the green stuff, all we're using is just the last mip-map level.
Okay.
And yeah, so I'm just gonna go back to RenderDoc. So oh god, I started another RenderDoc. Okay. So so basically, we don't even need to know anything about this whole thing, because I don't need to look at the page ID, the Y value, to know that I'm in a mip-tail. I can calculate it myself with this level in tail thing. And you can see I'm computing it up front before I enter this function, the v-texture helper v-texture helper. Fine, next. Okay. Okay, so this level entail, yeah. So I'm able to actually figure that out because I've got the original size of the texture saved into my texture handle.
Okay.
So, and also the original max full mip-map. So I'm able to compute which mip-map level I should be sampling from with this whole special stuff using the derivatives. And then I've got my, I figure out my high level of detail, my low level of detail, whether I'm actually in the mip-map range. If I'm, for example, too zoomed in, then I don't need to do trilinear filtering. If I'm, for example, too zoomed out, then I also don't need to do trilinear filtering. But I calculate this LOD, level of detail. I then clip it with this clipped LOD thing. I clip it to the count of stuff, of the levels of detail that are actually in the original texture, original max full mip. And then from the difference between the original max full mip map and the actual mip map that I want, I'm able to compute the level in the tail. Right? And then that's how I get all the stuff. So I don't actually need to query if page ID Y is valid to know that I'm in the last mip-map. Yeah. So generally speaking, I will send you the captures because they're quite useful to play around with. So for example, it's very useful to visualize certain stuff. So I'm gonna edit the shader and I'm gonna show you a few things. Okay, so we've got our texture viewer and I'm gonna look at the output, which is the back buffer color. Okay, so I'm gonna show you, for example, just need to find the color output. I can show you which textures I'm using. So I'm gonna comment out this for a second. And where's my out color? Out color.
Well, okay, but I still have a questions about the last mip-map level. What is special handling about it that we use? Why we cannot sample it like other mip-map level?
Because if you wanted a separate page for the mip-map levels that are smaller than the page, the problem is that there's not enough pixels in the page table, right? So it's not a problem of the physical storage; it's more a problem of the virtual texture. So if you look at the virtual texture here, right, you've got a certain problem, is that these 4 pixels right here I'm just gonna show them a little bit better. So this 4x4 area, it has a one page for every 128 pixels, and it's only belonging to this texture that got packed into here. And this is true when I'm going down in the, you know, in the what's it called, in the mip-map levels, right? I'm just moving the moving the stuff around to make sure they can see more clearly. But the main problem is that with this, right? When you're going down one more mip-map level, okay, yeah. So when you're going one more mip-map level, the problem is that this is the last time that this whole pixel covers that one texture that got packed. And as I'm going up and up higher, so I'm going up higher, right? We start running into a problem. Because there are other textures here which would get squished into that one texture. They're not allocated, this is why you don't see the squishing, but you know, like if you go here, that once I start halving the size, the problem is that this texture, which is a small thing, and then this empty area around it, plus those other textures which are bigger than it. Right now I'm on 8x8 texture, right? But if I actually went up, you know, the mip-map levels higher, they would all get mushed into one thing. And every single one of them would basically, you know, need its own page table. So it's not page table, but its own tile, right? So right now I have some unallocated space, but I have 4 textures in this area, right? And by the time we get to a page table which has a mip-map size of 1x1, right? I would have to have 4 separate tiles or even more for 4 separate textures to store the, you know, the some mip-map level, but I only have 1 pixel in the page table. So it wouldn't be possible.
Still a little bit complex for me. Maybe I'll ask later when I implement it.
Well, basically, it's to do with the fact that you'd have to squeeze lots of textures into one page table entry.
Okay.
But you can only have one page table entry for one texture. Even the thing that I'm doing with where I have 2 page table entries for one texture, right? For one pixel is a bit of a stretch, but I cannot scale it up to have, you know, because
okay, so
here
it has to do with it has to do with when you need to pack all the mip maps level into one tile, right?
Yeah.
Okay.
That's it, because the size of the original texture with all of its neighbors would be less than 1 pixel inside the virtual table. So you'd have to you start having an overlap, and then you wouldn't be able to record all those values, all those allocations.
Okay. So well, what is the thing that you call mip-tail handling? The tail is the last level, so
yeah. Basically, I'm calling it the tail because it's like it's the last levels of the mip-map pyramid, which gets smaller and smaller and smaller. And
it's the one by one texture, or
it's everything that's smaller. It's everything that's smaller than one tile. So it's if your tile size is 256, then it's everything that's smaller than 256. So it's your 128, your 64, your 32, your 16, your 8, your 4, and your 2 and your 1.
Okay. So the tail means everything behind the original size, right?
No. Everything past the the last mip map which has a size equal to or bigger than a single tile. So a 120, sorry, so a 1K by 1K texture, which is the case here,
Okay.
right? A 1K by 1K becomes 4 tiles,
Yeah. Yeah.
right? Yeah, so this is this is 4 tiles here. Sorry, 4 by 4 tiles, so 16 tiles, right? And then
Okay.
when you go to the next mip-map level, it becomes exactly half that, yeah? 2 by 2, okay? And then when you go to the next thing over, it becomes a 1 by 1,
Yeah.
right? On the very, very last thing. Yeah?
Yes. Yeah.
And then the problem is that once it becomes 1 by 1, it cannot go much smaller than 1 by 1, right?
Yeah.
Can't go in fractions. So then I need to deal with all of the stuff that is smaller than this 128 by 128 last mip map. That is has a
Okay.
whole page table to itself, right?
Okay. Okay. So when it gets to the point that the page table only store one tile in one pixel,
Yeah.
at that point you will have to combine the mip maps. You know, well,
Yeah, exactly that.
we
So
yeah, okay. You have to insert the mip map levels into that tile.
yeah.
Yeah.
So that's the last one,
Okay.
and then that's all of the
Okay,
stuff
okay.
that you need to pack.
Okay.
So yeah, so I can visualize for you a few things if you play around with the shader. Obviously, all of the source is online. You can compile it and so on. It should build quite nicely. So
Can I run it on Linux yet?
no, not yet.
Okay.
But it builds out the box on Windows pretty much. So if
Yeah, so you can send me the capture later.
the captures should run on Linux actually, I think.
Yeah.
You just need to, you know. I don't need to do anything actually. So, for example, I can visualize to you the layer that it's using.
Okay.
So I'm gonna do it like this. So if the layer is 0, then it's gonna be red. If the layer is, because there's only actually I'm gonna do it like that. Okay. So there's only about 8 layers of the virtual table being used.
Okay.
So I'm gonna refresh, and you can see the different layers that are being used.
Okay.
See?
Yeah.
So you can see that the windows and the door is using a slightly different layer of the virtual table
Yeah.
than the columns, and obviously the floor is using, I think, layer number 0, I believe,
Yeah.
from the virtual table. I can also show to you which texture format it is using. So, for example, okay, I'm just going to do. Okay, so I've got this format, and then if this format is 0, if it's the very first format, but I know none of them will be, then it's red. And then if it's format number 1, which would be your RGB texture with no alpha, then it's going to be green. And if it's format number 2, then it's going to be blue, right? So you can see that the walls are using texture with no RGB, but the floor is using a texture with RGB.
Okay.
Sorry, so it's using the the top stuff, the green stuff is the stuff with no alpha. So it'd be it wouldn't be this texture, it would be the other one, and then the blue stuff is the texture, this texture here, right? And then we can visualize some other stuff, like for example, the original texture sizes. This is quite fun. Because of all this padding to powers of 2 and everything like that, and the fact that the original texture is actually smaller than the texture that you've padded it to, my handle actually needs to store the original texture size and a whole bunch of other stuff. I'm actually going to show you quickly in the C++ side of the whole thing what it's actually going to be using. So my virtual texture here is that in the first 32 bits, I actually store the original X and the original Y size of the texture. And this is not in tiles, this is not anything else, it's actually in full texture size.
Okay.
So this, as you can see, obviously limits the size of the texture that I can pack into the virtual texture. The original size of the texture, that limits it to 16K by 16K.
Okay.
That's the max you can pack into the virtual texture, which shouldn't really be a problem. And then the second 32-bit actually contains, the offset into the physical page table, the physical storage. It also holds the maximum mip-map level of the original texture, but with all of the padding and the rounding up applied. And it also holds the wrapping modes of the texture coordinate. Because remember that if a wall was repeating, for example, like in this model, then the UV coordinates were bigger than 0 and 1. So I need to know how to wrap them, and I reserve 2 bits for that. So I know whether I need to mirror them, I know whether I need to repeat them, and I know whether I need to clamp them. Right?
Okay.
So that's kind of important. So I can show you the virtual texture reciprocal size. The reciprocal size of the virtual table. Okay, I know why that is. That's actually not too interesting, actually. Yeah, that's just going to be black. I can show you the maximum mip-map level of the texture. Okay, so I'm going to show you the maximum mip-map level of the texture. So as you can see, all of the textures were roughly the same size. So there's nothing here to show as well. The wrapping mode, but I think it's the same for all of them. Okay, yeah, I can show you the original size now. It's going to be in floats, so it's going to be quite a big value. Interesting. One second.
It's not refreshing.
Yeah. Okay, so for unpack size. Okay, interesting. Does it get cold? Unpack size. It does get cold. Okay. Interesting. Okay, so physical page table, unpack page ID. Oh yeah, I can show the page IDs. That's also cool. Yeah, so here you can see all the page IDs that have been mapped.
Okay.
So this is basically you seeing the virtual table textures. It's the virtual table being textured onto the geometry.
Yeah.
Yeah. It's pretty useful. I can also put in the curtain as well. Yeah. Obviously the notable thing here is that you can see some discontinuities, but those are due to different mip-map levels being picked. Because obviously when you've got those like edges that are at an angle to the camera, it goes to picking lower resolution mip-map levels.
Okay.
So yeah, so that's here. And obviously I can show this vtable helper. Sorry, the virtual texture helper. So, for example, I can.
But the plans isn't using virtual texture, or
No. It's just a different shader because they're using a shader with alpha testing. They're still all using. I think they're still all using virtual texturing. It's just that the plants are using a different shader.
yeah.
So I'd have to edit the different shader. So yeah, I mean you can see a lot of stuff here. I mean you can for example see which pixels need to do trilinear filtering and which only have to sample one mip-map level. So I can for example show you that some pixels need to do trilinear, some don't, and I'm going to show you which ones need to with red. So here you can see that most pixels need to do trilinear filtering except for the ones in the columns. I think because they're sampling from really high resolution mip-map level, because I think the texture got stretched, so they don't need to do trilinear at all. You can, for example, visualize the level of detail. So the clipped level of detail in our case here is going to be this, and I'm just going to do effective. And I'm also going to show you the level in tail if they're past the level. Okay, so you can see which mip-map level is being used. So 0 is full resolution, and then this kind of dark red is, I think, one mip-map level up. And you can see here that because of all the bends in the curtains, the mip-map level actually went up by one level, right? And obviously on these bars here, which are an angle and have really tiny geometry and stuff, then the mip-map level is actually quite high. And you can see that it's beginning to be green. See, there's this green here. And what it means is that when this green appears, is that it's actually starting to go into the mip-tail, right? So you can see that here we are starting to sample those really, really small images from the mip-tail, where the green is, right? Well, where it actually turns yellow, yeah, but there's obviously green there. So yeah, so you can see that. Yeah, The other thing to see would have been the obviously you see which mip-map level is getting picked. There's two modes in our original code in the shader. There's one where you use what's called very accurate anisotropic calculations, where you actually use what's called square root to find out the length of the axis of the ellipsoid, which gets projected into texture space. The thing that I was explaining on the last video. And there's one where you just basically use the Manhattan distance, which is just a sum of absolute values of the coordinates as an approximate of the distance. So it's a little bit faster, but there's an option for both of them. And yeah, I mean the whole function basically takes apart and implements texture, what's it called, texture gradient function from GLSL. So theoretically, when you're implementing your virtual texturing, first you shouldn't worry about the virtual texturing at all, but worry about this manual texture grad function, right? So you get all of the derivatives right and the mip-map levels right, and then go on to the virtual texturing. It'd be just easier to do it that way. Yeah, and then the last final thing I can show to you would be the mixing between the what's it called, the two mip-map levels. So this is the relative weight of the mip-maps. So you can see that where it's dark, it's taking more of a value from the lower mip-map, and when it's white, it's taking. Sorry, when it's more white, it's taking more of a value from a lower resolution. When it's black, it's taking more of a value from a higher resolution. But that's between the two mip-maps, and if you actually want to see the LOD parameter, the fractional level of detail, then what we need to do is just have a look at this. And this is showing you the mip-map level that you'll be using here. So when it's darker, it's higher resolution. When it's brighter, it's lower resolution. You can see it gets really, really bright on all the small details, like here, and especially surfaces which are at an angle. So yeah, I mean, on all of the captures, you can pretty much take apart and show every single part of the whole process and compare to a working original. Yeah, I mean, aside from that, you can also modify the source code to spit you out the shader before it goes into SPIR-V. Sorry, before it goes into GLSL Lang. Because that shader is slightly more legible than a shader that's been compiled twice. Any questions?
Well, we have covered a lot of technical problems in implementation, but I certainly cannot remember it all, the handling specifically, but what I understand is the list of what needs to be implemented. So I paid attention to the key topics of the whole implementation, so I can implement it and research further when I implement.
Yeah, the good thing is that if you actually do your allocators the same way that we did, as in I mean, it shouldn't be too hard with the pool allocator and stuff, Maybe the general purpose allocator. I think your physical textures should actually look the same way that ours do. As in, after you see the packing, everything here should be basically pixel for pixel the same.
Yeah.
With the relative positions of stuff. And also, like, I mean, if your allocator for the virtual table is similar, then your virtual table should look the same as well.
Yeah, yeah.
I think. Because as long as you're not allocating and deallocating, you shouldn't really get allocations in different places.
Yeah.
Or even with
Right.
different numbers. Because if you're
Yeah.
using Mortem codes and you're doing all of the alignment properly, then you're allocating from the front. And there's only one way that you can get all of the free slabs from the front, right?
Yeah.
So I think all of the values should basically be like identical.
Yeah.
As long as you basically do a test run and pack your textures in the same order.
Yeah. But you know, the texture loading process and texture format, it can affect the values too, right?
The only thing that's going to affect the values that you get here is the order in which you request allocations. Because in our implementation, what happens is you request an allocation in the virtual table, but the virtual table doesn't get any pixels written yet. So basically, the allocation only tells you which pixels have been assigned to you, right?
Okay.
And as long as you make all of those requests in the same order, as in first you ask for a texture which is 512 by 512, and then you ask for a texture which is 2K by 2K, and you know, with the same formats and stuff, right?
Yeah.
Then all of the placements of the textures are going to be the same,
Yeah.
as well as all of the layer assignments. You know, which layer of the virtual table goes to which format, right? As you can see here. So that's all going to be the same, except that so that's all going to be the same. And then our implementation then works like this, that after you allocate, then you commit, then you ask for a commit. And when you ask for a commit, that's when the data actually gets copied to the physical texture, and the coordinate of the place where it got copied to in the physical texture gets written to the virtual table. And as long as you use a pool allocator, which has a stack, and the stack of free tiles has been filled backwards, so the higher addresses, the higher free addresses are at the bottom of the stack, and the lower addresses are at the top. So you start allocating from the front, and you're using a snake order curve, not a Z order curve. You know, just going, you know, left, right, left, right, left, right, and using the same mapping of address bits to coordinates. Then you will actually get the same values. You'll get the same tile allocations as we do.
Yeah. I think I'm gonna consider how do I use the layers, because you know, well, I think maybe just I won't use, you know, 3 different formats for texture, and maybe I would just have one physical page for every kind of texture. Maybe it's gonna waste some you know, memory when that, but you know.
Basically, what we did is the first prototype that we had working, that I shared captures for, that had only support for one format. But then we found that it's actually really easy to just extend it a little bit and have support for many formats. I can support as many formats as there are texture bindings free. So if there are 16 texture bindings like in OpenGL, then I can use 15 formats, right?
Yeah.
It's not really.
Yes, so maybe I will extend more formats later, but first I will have a working version, one format.
Yeah.
Uh,
I think our code is really easy to copy and adapt for other purposes. So we have we have 3 classes, 5 files, and 1 big GLSL include. So we have all of the code that you need with overrides. So if your engine doesn't work exactly the way our engine does, you can just define a preprocessor thing, like for example, I don't know, for example, this thing, float views count and stuff like that. All of those if-defs, you can define yours up front before you even include this in your own application. Then it will basically change the behavior. You can even replace entire functions. The only thing that would need some adaptation is just this non-uniform qualifier thing. The thing here that does all of the subgroup stuff. And aside from that, there's only one place, 2, 3. Okay, so there's only 3 places that needed changing, really. And as far as prototyping, getting this running on the desktop, NVIDIA AMD, you're gonna have that non-uniform extension anyway, so that's pretty much your last concern. But this whole entire header that we have in our engine, you can pretty much get and use your own. There's 3 headers that we have. There's one called so it's gonna be air GLSL virtual texturing. Air / built-in / GLSL / virtual texturing, and then the path for that is going to be functions, extensions, and descriptors. There's basically 3 GLSL includes, and the way that gets used is it gets used pretty plainly, except that you need to define a few things. So the only things you need to define are in the main of the megatexture example, which are the which descriptor set and binding you're going to be using for the virtual table, for the floating point format views, and for the integer format views, because as you know, they have different basic types. The floating point stuff is just a sampler 2D array. The integer stuff is an I sampler. The unsigned integer is a U sampler. And then after that, you include the descriptors. And then you obviously you put the extra data that the stuff needs in your own SSBO. So the log base 2 of the page table size, the reciprocal size of the virtual texture, and then the reciprocal sizes of the physical textures. But this is an array in terms of the layers of the virtual table. So it's not an array for all of the samplers. It's more of a first you use this layer to sampler index mapping, and then from using that you can put this together with this thing. So it's basically for every single layer of the page table, you've got a physical texture assigned to it, which can be different sizes, because you might not need as much memory for a different texture format, which you don't use very often as you do for another. Knowing the layer of the virtual table, then that gets you the physical page size. And then you basically need to define these 4 functions. One which translates the virtual table layer to an index into the descriptors for the texture views. One which gets your logarithm to size of the page table. One which gets you the reciprocal size of the physical texture given a layer. So layer maps to physical texture index, and then that physical texture you need to have the reciprocal size of that. And the virtual texture, the page table, together with the tiles, the big texture that doesn't exist, the size of that. And then you define that the user has provided virtual texturing functions, and then you include the virtual texturing functions GLSL. And then everything is fine and dandy. It's not really a whole bunch of stuff that needs to be added.
Okay.
And that whole thing you can lift and pretty much paste into any engine. The GLSL doesn't need that much modification. The other stuff we have is we've got this virtual texture class, which handles all of the packing. Obviously uses a lot of our engine API, but I mean it has all of the logic that you need, essentially.
Yeah.
So it's 1,000 lines of code for the base, and then there's a separate class for the CPU virtual texture and a separate class for the GPU virtual texture. The GPU virtual texture doesn't support adding and removing textures at runtime. That's a thing for the future. Right now, what we do is we make a CPU virtual texture, we prepare all the stuff, we pad all the stuff, we put stuff in, and then we use the GPU virtual texture created from the CPU virtual texture, and we don't do anything to it. We just leave it laying around. But there's a lot of stuff that will look very familiar to Vulkan. Like for example, get the descriptor set right. Gets you all the descriptor sets that you need to write. Gets you layout bindings. Stuff that's quite familiar with Vulkan. Obviously, there's a whole thing with aliases, where, for example, you would want to use the same texture but with two different formats, so you don't need to allocate the memory for it twice. So, for example, if you want to use the same texture as an sRGB and as an RGB at the same time, and because the pixel formats are compatible normally in Vulkan or OpenGL, you'd be allowed to make two texture views of it, right? So, in this case, what we allow is basically, first of all, you can allocate, you can commit the texture, and that's handles of the memory, but you can also create an alias, which basically makes a page table entry on a different layer for a different format, and it copies all the pointers from a different layer, so you can view the same physical texture with the same memory as two different formats, which can be quite useful. And I mean, aside from that, it's not really complicated. I mean, you've got all the allocator stuff, and then there's basically these last 100 lines of code, which basically tell you how to pack mip-tails, right? So it's a little bit of very useful code that basically you tell it the base 2 size. So 0, 1 by 1, 1, 2 by 2, 2, 4 by 4, yeah. And the padding, how many pixels of padding it has, and it will spit out the rectangles of packed mip-maps. Yeah, and that's basically what we use to figure out all this how we pack the mip-tail, because we can we haven't hard coded the padding, or we haven't hard coded the page table size. So it can work it all out for you. So I mean, if you know what you're doing, it's pretty much a copy-paste exercise. The only thing that you might encounter problems with is stuff to do with allocators.
Yeah.
Like the GPU stuff isn't like the GPU virtual texture thing is basically 180 lines, where it's basically mostly about copying stuff from the CPU equivalent.
Yeah.
And the CPU virtual texture actually handles only two things extra. It handles this thing, create power of 2 padded square image with mip-map levels. So it'll actually do this very painful and laborious thing where you take an image which has an arbitrary size, it will round it up to a power of 2, make it a square, apply the wrapping, apply the border color, and it will do a padded copy.
Yeah.
And it will do all of those repetitions of the image that I've been talking about at the very start of the video. It will do all of the repetitions, and that will generate all of the mip-map levels.
Yeah.
And that will return you the image which has now been grown to a square and a power of 2, plus the original size. As a pair. Yeah. And the other thing that the CPU virtual texture does is that when you do a commit, which actually has to do with the memory, it will actually copy the data over. So it will copy the data from the image, which is now has to be a power of 2, this one that you pass in, and copy that to tiles, apply all of the padding that you need for anisotropic filtering. That's why we've invented this padded copy image filter, which can actually do the copies which have borders. I don't know if you saw it in the physical texture. In the RenderDoc captures, I'm just going to show it really quickly to you. Best place where it's really apparent is actually just looking for a place where it's really visible. Okay, right. Maybe no. Okay. Okay. I guess we can do here. Obviously, you can see that between top and bottom there are discontinuities, but I want you to have a look at the discontinuity. I want you to have a look at the discontinuities between the left and right, right? So you can see that here we've got the band of 8 pixels repeated.
Okay.
Yeah, 8 pixels repeated here, and then 8 pixels repeated in this tile, and then same here. You've got 8 pixels repeated on the left, 8 pixels repeated on the right. Yeah. So it's doing the padded copy filters, with extra pixels. So there's some overlap for the anisotropic filtering. So so that's basically how this whole thing works. Is that in this little function we get a padded copy for every single tile. And then some stuff to do with the create alias, so basically copies your virtual table pixels. And that's pretty much it. I mean, it's not a whole lot more. It's only 400 lines extra from the base. Yeah, so it's not a whole lot of files actually to deal with.
Yeah.
Well, about the implementation, I think I will study your version and actually make a simplified version of me, because I think that I can make it a lighter version, maybe.
You can cut a lot of corners if you decide to use one format and keep all of the textures square and power of 2.
Yeah. And for example, the image processing part, I can use I can implement it using an external library, maybe the CEMG library. Have you heard of that?
I don't know of a library that can apply wrapping modes plus wrapping modes plus what's it called? Border colors. I would have used NVIDIA texture tools if it wasn't for the fact that I would have to wrap and border color my images first. So I think you can always do it by stretching images to power of 2 and square, but you're going to be wasting a lot of memory. I mean, but if you don't have
Yeah,
that
yeah.
many, if you don't have that many images which aren't really square in aspect ratio, it's not going to be a big problem.